o yüzden.
O zaman bana işaret ver başladığın zaman.
Okay. Hi everyone. Today we are starting with Ito calculus, as you know, and our first lecturer is Süleyman Üstünel from Bilkent University, and he is also organizer of this lecture series. And if you are interested in these topics and if you have not registered, please visit our website. Is there anything you want to add, Hocam?
No, it's okay.
Not? Okay, if not, we can start. We can start, Hocam.
Okay. So I will be speaking, as I have tried to say before, in English. Not that my English is better than any other language that I know, but my knowledge of mathematics dictionary is much better than than in Turkish. That's why I am choosing English. Well, I could have spoken in French, but we are not in a French-speaking environment. Okay, so when Sabancı Club of Mathematics has proposed me to speak about the Malevin calculus, I asked them if they were introduced somehow to a kind of abstract mathematics concerning, for instance, little function analysis, measure theory, etc. They said no. Then, it was clear that for them to be able to master the Malevin calculus, they needed some heavy background. That's why we have decided to begin with the most important part of the necessary material, which consists of an introduction to Ito stochastic calculus or Ito stochastic analysis. Okay, and since in Turkish universities the measure theory is not taught really very well, I prefer to begin with basic level of abstract measure theory. Abstract refers to the fact that we don't use any topology when we define the integration. As you know, or you may not know, generally, when you look at the classical analysis books, they begin with the concept of outer measure in real line, which uses the concept of open set times topology. Okay, so here we cannot use this. I will explain why. So let me explain you with an example, concrete example, what I have in mind. Suppose that we are coin tossing. So we are tossing a coin and we are going one unity to the right on the real line if it is head, or one unity to the left if it is tail. Okay, and we are giving so the numbers plus and minus 1 to the outcomes of tossing, and we are looking at our position in the real line after n experiments. So I will denote by Sn our position after n toss. So it is equal to sum from 1 to k, 1 to n, xk, where xk takes the values in the set -1 + 1. Okay, this is with probability 1/2, let's say. So it's a fair coin. This is called elementary random walk. there is a famous theorem of Donsker and Varadan, which says that Donsker and Varadan was the student of Donsker, Varadan from Courant Institute, which says that if you take 1 over square root of n and you sum these people k from 1 to n times t, t is being our implicit time, and I am taking it is integer part. Then you look at this xk and look at the limit of this thing as n goes to infinity. Donsker-Varadan theorem says that this is equal to Brownian motion. They call it Bt. Well, this limit, of course, it requires some definition. So this limit is the limit in the sense of convergence in law. It means that, so the meaning of the limit says that if you take any continuous and bounded function on the real line f, and you compose it with these people, so s and t divided by square root of n, and you take its average, okay, so average of this, average with respect to coin tossing, then this average converges as n goes to infinity to the integral on R of the function f of t with respect to Gauss kernel. Let's say put x here, x squared over 2t dx over square root of 2 pi t. Okay, so this is heat propagators, or fundamental solution of the heat equation, it's called. Anyway, or we call it Gauss kernel, and I will define this P T sub F. This is a famous theorem. And this PT, or this thing, governs the random variable, which is BT, and BT is called the Brownian motion. In fact, theorem is much deeper. It says that with probability 1, whatever it is, we do not know yet, but the function as a function of time, BT, at the point omega, which is, this is the point of randomness, is a continuous function of time, is continuous from positive real numbers to R. This is a deep theorem, and this thing was known more or less since the period of Norbert Wiener. Also, PT is sometimes called Wiener process, okay? Now, the things get interesting when you look at this function. Suppose that we begin from the initial point, small x here, or small psi. So this is, I will denote this psi. And if you look at this function as a function of t and psi, p t of f of psi, and I will denote it by u t comma psi, this function satisfies an equation which is equal to partial derivative of this u with respect to t. This is u, and this is parenthesis, is equal to 1 over 2 Laplace operator applied to the space psi u t psi, with initial condition u0 psi is equal to function f of psi. Hence, this is the solution. I mean, this is the Cauchy problem for the heat equation. And if instead of doing this, I put here, let me see, if I can put here, instead of doing this is the first level. Second level, I can put here a supplementary term, okay? I can put a supplementary term. In the above equation in I of the form like that. Let me in such a way that such that the equation reads, equation 1 reads as follows: du over dt this time is equal to 1 over 2 delta u minus v times u. V is a given function. It is generally assumed to be positive. I will say measurable, but we don't know yet what the measurable is, so I will not insist too much. And with the same initial condition, u0 psi is equal to f of psi. As you see here, V acts as the heat source in physics. And this is the heat equation with a heat source designated by V. Okay, this is the second development. And the third thing, instead of taking, I will come to this situation. How do we insert this? I don't want to come back to the limiting coin tossing problem for this, but we shall obtain this. This is obtained very easily from Ito formula, which will come, okay? So be a little bit patient. But suppose that I put, instead of BT, I put square root of lambda times BT, lambda being a constant. Okay, so then this equation will read du over dt is equal to then lambda over 2 delta u minus v times u. Okay, I didn't do something very interesting apparently, but if I can replace lambda, instead of taking real constant, I put here square root of -1. So this becomes Schrödinger equation. Then the equation, this is, let's say, 2 is the Schrödinger equation of quantum mechanics. And this observation has been done by Richard Feynman. It should be the 60s. Anyway, he has received the Nobel Prize of Physics at 64, I think. I'm not sure about the 4 or 7, but this is Nobel Prize, Nobel in physics. And in fact, well, this is a little bit optimistic situation. Well, if V, for instance, is not a very special type of function, this thing is only formal, but nevertheless, it gives all the numerical calculations exactly. Okay, it's a mystery why it works still, but we are passing from the heat equation to the Schrödinger equation. The physicists call the time of the heat equation complex time. Mathematicians call the time of the Schrödinger equation complex time. Okay, so there is an opposition here. Nevertheless, well, this is the situation. Now, at the year that some 10 years later, two economists, they were trying to read the work of Bachelier, Louis Bachelier, who was a French mathematician, Bachelier, who was making his thesis at the 1900s, and he was trying to modelize the stock prices by using the above Brownian motion. Okay, so he tried to apply BT to modelize stock prices of the stock market of Paris. Okay, and he has written a PhD thesis about this thing, and his thesis has been rejected, saying that, well, Brownian motion gets negative values with high probability, though we cannot imagine negative valued stock prices. And this has lasted until 1974, when Black and Scholes or Scholes, I am not sure about the pronunciation, the letter is, and I think he's from Scotland, so I'm not sure about it. Okay, and they have proposed, instead of taking Brownian motion like that, they have taken just exponential function, applied this exponential function to our Brownian motion that we have constructed at the beginning. They have put a constant here, sigma, and minus, they have subtracted sigma squared over 2t, and this was to modelize the random part, I mean, uncontrollable part of stock prices, and they have added also an exponential deterministic term R times T in such a way that they have modelized this, and they have tried to apply this to stock market. And with this, they have received 96 Nobel Prize in economy. So as you see, this subject is extremely hot again. And not to mention about the other applications, because we shall be losing too much time, but when the time will be ripe, I will explain some other examples, of course, of this kind, okay? So in this series of courses, we shall be trying to understand these phenomena, especially the real mathematics, which is necessary to understand these things, okay? So as you see, I am always talking about the randomness, hence I have to speak about the notion of random variables and their average, okay? So this means that we have to speak about probability. And to calculate the expectation or average of a random thing, we have to know some kind of integration. But the integral in finite dimensional stuff is not enough for us, because when you look at this model of Black and Scholes, you look at the stock price ST as a function for t varying, for instance, between the time 0 and capital T. Capital T is called, by the way, the maturity in economy. And we look at this as a random variable. So it is, the randomness is omega. It is mapping the omega to these people, to this bunch of functions on 0t. So what we are doing, in fact, we are defining a random variable. Let me call this S. S is a random variable from some space of samples into the space of the continuous functions on 0t, with values in real or in the vector space, well, you don't have to need only one stock in your portfolio. So I'm very often tempted to take RD value things. Okay, so we are looking at the random variables with values in infinite dimensional spaces. Okay, hence in this setting we need to make some integration and we need to calculate averages. This requires a whole different set of measure theory tools. This is what we are going to do. Today, we shall begin. I hope that we shall be equipped well enough in 4 or 5 sessions, hopefully. I will give everything from zero. Okay, so let me begin here, measure theory. For measure theory, we begin with an axiomatic triple. There will be the space of samples or the space of randomness, omega. Okay, so this is the sample space. We shall take later function spaces as sample spaces, but infinite dimensional each time, and we shall need them to be vector spaces at the same time, for instance, if you want to make variable calculus, okay? And we shall take a probability, P will be a function from a subset, of the power set of omega. Power set means the set of all subsets of omega into the unit interval 0, 1. So this subset, you cannot choose any subset. This requires some very precise properties to construct an integration theory which is valuable and efficient. Hence, here comes the notion of sigma algebra. Okay, sigma, so we shall define, then P is a function from this curled F, which is a subset of P of omega with values in 0, 1, where F satisfies the following properties. The first thing is that empty set should be, empty subset of the omega should be an element of F. Remember, F is a family of subsets of omega, okay? Secondly, if A belongs to F, then non-A or complement of A belongs to F also. And the thirdly, if I have a sequence, AN, subset of F, then its union from 1 to infinity is again an element of F. Here I draw attention to the fact that these sets are all countable subsets, countable sets, okay, because they are indexed with the natural integers. So it is forbidden to assume that arbitrary union of elements of F are again in F. This is a main problem or main issue to memorize, okay? So don't forget this. This is very important. This makes the life at the same time easier and a little bit more difficult. And such an object is called, F is called a sigma algebra. Sigma algebra. So I am writing, this is capital sigma Greek letter, red sigma algebra of subsets of omega. example, to see the example, the simplest examples, let's say. The first one is if I take F to be empty set and the whole set omega, then this is a sigma algebra. Another example, take any subset A of omega, then let F to be empty set A complement, and omega. This is again a sigma algebra. Okay? Again, a sigma algebra. Okay, these are trivial examples. A little bit less trivial is the following fact. If F and G are two sigma algebras on the same set omega, are two sigma algebras on omega, then their intersection, F intersection G, is again a sigma algebra. So this is the subsets of omega, which are belonging to both, is again a sigma algebra. The proof of this is straightforward, so I'm not doing it, okay? The thing is that we can make these things more complicated if, for instance, is a subset of the subsets of omega power set, then we define the sigma algebra generated by C. This is the notation, and definition is the intersection of all the sigma algebras on omega containing C. This is a very important concept, and it is called the sigma algebra generated by the family C. C itself, of course, is not necessarily a sigma algebra. Otherwise, if it were sigma algebra, then sigma C will be equal to C, because intersection means the smallest sigma algebra containing C. If C is sigma algebra itself, then they are equal. Okay? And this gives us a lot of examples of the sigma algebra. Example of these examples. This is a very important example. Let then omega to be the real line, and let C be the open subsets O subset of R open. Okay, then the sigma algebra generated by open sets of the real line, this is called Borel sigma algebra. This is a famous sigma algebra, Borel sigma algebra, due to the name of Emile Borel, sigma algebra, and it is denoted by script B, curl B of R. So since a sigma algebra is stable by complementation, we can also show that, in fact, this Borel sigma algebra is also equal to the sigma algebra generated by the closed subset so far. This is trivial, okay? And this is one of, we can also do this in higher dimensions. If omega is equal to R to the n, for instance, then we shall denote the corresponding Borel sigma algebras by B of R to the n. This is again Borel sigma algebra of R to the n. Okay, so for the moment, I will stop talking about the sigma algebras here, and I will give the definition probability space. Okay, so a probability space let me write it. It is a triplet which consists of sample space omega, a sigma algebra F, and a probability P, and P is a function, is a mapping from F to 0, 1. As you see, I didn't define P on all the subsets of omega. This is a very important distinction. In fact, we cannot measure the probability of any subset of omega. This is not possible in applications. For instance, in the real line also, I don't know if you have seen it, but you cannot measure the surface of all the subsets of real line, or area or length, whatever. Okay, so there are the sets for which this is impossible, and you construct them by hand. This is abstract stuff using axiom of choice. It's not easy to find, but there are. Okay, so the definition of probability in this situation is given, so it's called a probability. A probability. If the first condition is that probability of omega is equal to 1. And the second condition is if ANs is a sequence chosen from F of 2 by 2 disjoint sets. Then probability of the union from 1 to infinity of AN is equal to sum of the probabilities of each AN. This is the main difference with respect to elementary probability, which is taught in the second year engineering classes. Okay, this thing here up to infinity is fundamental to construct a reasonable theory. And this has been remarked by Alexander Kolmogorov in the years 30s, in 1936, I think. And Kolmogorov has realized that with this hypothesis or with this definition, he could construct the notion of average of reasonable functions. Reasonable means measurable. I didn't define it yet, and I shall define in soon, not immediately. But let me speak about first some elementary properties of this definition or consequences of this definition. Okay, so the first thing is that, so properties. P is positive. Okay, so the first property, if A and B are two elements of F such that A is subset of B, then we have probability of A is less than or equal to probability of B. Well, this follows from the following. Let me give the explanation. I can write B as A union B minus A. And as these two sets are disjoint, probability of B is equal to then from the second definition, probability of A plus probability of B minus A. Okay, hence, since this is non-negative, this should be greater than this one. And in particular, as a subproduct, this implies that probability of B minus A is equal to probability of B minus probability of A. Okay, so this is one thing. And the second thing is, if then instead of taking AN's 2 by 2 disjoint, I can take a sequence of subsets of omega from the sigma algebra and increasing sequence. Assume Cn as a sequence is a subset of F, and Cn is less than Cn plus 1, less than or equal to Cn plus 2, etc. Okay, both-sided. Then I claim that probability of union from 1 to infinity of Cn is equal to limit as n goes to infinity of P of Cn. This is a very important consequence because this helps us to approximate the probability of complicated sets. And we shall see a lot of applications of this to found an integration theory. Okay, so let me explain how we do this. We can write union of Cn from 1 to infinity, hence this is equal to C1 union C2 union C3, etc. Okay, I can write the same union as the union of disjoint sets. So I can write this also as C1 union C2 minus C1 union C3 minus C2, etc. This is the same union, okay? Because I am adding and I am subtracting the same set. Hence, the probability of the right is equal to probability of the left. Both are countable unions. They are measurable in F, etc. Hence, this probability 1 to infinity of Cn is equal to probability of union from 1 to infinity of these people that we call this C2 prime, C3 prime, etc., C1 prime, Ci prime. Okay, but since Ci prime by 2 by 2 disjoint, this is equal to sum from 1 to infinity P of Ci prime. In particular, this series is convergent, and we have just seen above that probability of Ci prime. We can write this then like that as n goes to infinity, finite sum. And P of Ci prime can be written as from 1 to n, then probability of Ci minus Ci plus 1 minus Ci. And since Ci is less than Ci plus 1, this is equal from consequence that I have written from 1 to n, then probability of Ci plus 1 minus probability of Ci. And when you look at this sum up to n, these minus terms cancel each other with the preceding plus terms. So this is a concentric sum. This is equal to limit, then n goes to infinity of probability of Cn plus 1. Okay, this is exactly what we have claimed here. So this I will use these properties. That's why I am touching them, and I want that you to be acquainted a little bit more with more intimacy than just as a spectator. And counterpart or alter ego of this result is the other way around. So this was, let me see, second property, third property. Assume that we have a sequence of measurable subsets of omega, hence from F, such that Bn's are decreasing. So B1 is greater than B2, is greater than B3, etc. Okay, then I claim that probability of intersection from 1 to infinity of Bn's, which is a measurable set again, hence the probability of it is reasonable. This is equal to limit as n goes to infinity of P of Bn. And I just would like to draw your attention, this limit, this sequence is decreasing with n. So sometimes I will put some arrow here going downward or upward, indicating that it is increasing or decreasing, okay? And the proof of this is the alter ego of 2, okay? Follows from 2 by complementation. Okay, so this is essentially what we want to know about a probability space. Now I will speak about the random variables. And hence I will say that okay, let me come to random variables. Well, we know that what a random variable is from engineering courses. Well, we shall be a little bit more rigorous here. We say that X, a mapping from omega to real line, is a random variable with respect to the sigma algebras F and omega, here F, and here Borel sigma algebra of R, if any subset which is a Borel subset of R has an inverse image which is an element of F. If for any here. This is the check. So X minus 1 of B, as you know, this gives you, this is defined as the set of omegas in the first space for which X of omega falls into the set B, which is in the second space. The inverse image of B under X, okay? So in this case, then we say that X is a real random variable, abbreviation. Okay? So with these random variables, we shall define the notion of integration. We shall try to calculate the expectation or average of a random variable. Well, we shall first, let's say, concentrate on the positive random variables, then we shall generalize it using this sigma algebra stuff, okay? So the first step in this calculation of the averages will begin with the elementary random variables, which take only a finite number of values. Okay, so this requires a small definition. So this is called step random variables. Or simple random variables. So this means that X is measurable from omega to R and takes only a finite number of values. Let's say X1, Xn. Okay, hence I can write X of omega as a function as to be equal to sum from 1 to n xi times the set on which it's equal to xi. This is the indicator function. So, oh, I forgot to say, let me call it a reminder. If A is a subset of omega, let me take measurable, then the indicator function of A at the point omega is defined as the function as to be equal to 1 if omega is an element of A, 0 is not. Okay, this is called indicator function. Function of the set A. The analysts call it characteristic function, but I prefer to call indicator function because characteristic function is different in probability. It is the Fourier transform, etc. Okay, now, so when we have a simple function like that, then as we see, simple function can be written as a finite sum of constants times indicator function of measurable sets. Okay, this is a measurable set because we have this belongs to F, hence its indicator function is defined below, and it is this is well defined, no problem. Okay, so we shall define. So the definition. Okay, the crazy thing has arrived. As you see, somehow the tablet zoom out. Well, I don't know what happened. Okay. I don't know how to settle this. Okay. So if I have a simple real valued random variable, then I will define, so this is the definition. If x then, x is simple, then I define its integral on omega as the sum from 1 to n here, xi times probability of AI. I call these people AIs. Okay, this is the definition. Sometimes we shall denote it also by E of x, E as expectation. And if there are several probabilities, we put here an index at the bottom to indicate with respect to which probability we are calculating this expectation. Okay, let's make a water break, then I shall take at 6. Is it okay with you? Are there any questions?
Okay, hocam.
He?
Okay, hocam. Is there any question?
Anlamadım. Sorry?
There's no any question, hocam. We can give a break.
No question.
Okay.
Okay. Okay, isterseniz başlayabiliriz.
Before we start, can you explain one more time the relation between definition of random variable and Borel sigma algebra?
Definition of?
Random variable and Borel sigma algebra.
Okay. Okay. We say that a random a mapping X from omega to real line is a random variable or a measurable map, is a real random variable relative to sigma algebra F here and Borel sigma algebra B at the second space if any element of the Borel sigma algebra has an inverse image under X in F. This is the definition. Example. Let me take A subset of omega, which is in the sigma algebra F. Okay? And let me call X its indicator function. So X is a function from omega to 0, 1, which is injected into the real line. Okay? Hence, when you take the inverse image, özür dilerim, bir telefon. Alo. Evet.
Hocam, you are muted now. Can you unmute yourself?
Yeah, okay. Is it okay now?
Yes, it's okay.
Okay. No, I was saying that I have 4 COVID tests positive, so they are getting panicked. So if you take the inverse image of 0, this is equal to A complement, and inverse image of 1 is equal to A. Okay, hence X is a measurable function. X is a real random variable. This is the most trivial one. That's why I prefer to give it as an example. Okay? Is it okay or not?
Okay, hocam.
Did you learn how to define a continuous function? A continuous function, we say that a continuous function f from a space A to space B, the topological spaces is continuous if inverse image of any open subset of B is open in A. Okay, this is almost the same thing. Inverse image of any measurable subset of R is a measurable subset of omega. There is an analogy. Okay. Now, I come then to the definition of the expectation of a simple random variable. Then we have defined it then expectation of X is equal to value or the values taken with X 1 to n lambda I times probability of the set on which the x is equal to this value, lambda I. This is the definition, as we have seen in elementary probability also. Okay, now let me give some very simple properties of this expectation. Of course, I shall expand this these properties to non-simple random variables. For this, I have to know first the properties. So the first property is that probability of a set A is equal to expectation of its indicator function for any A in the sigma algebra of F. The proof is very simple. Probability of A, well, we know what it is. Expectation of A, indicator of A is equal to then value taken by indicator of A is equal to 1 if we are in A, and I am taking the probability of this set. So this is P of A plus 0 times probability of A complement. Okay, so this is, we are done. And this is the first property. Second property is that if X is a simple positive random variable, then its expectation is also positive. This is trivial. And thirdly, it is linear. Expectation of C times X, C being a constant multiplied by a simple random variable is again as a simple random variable, it is measurable, and it is equal to then expectation is equal to constant times expectation of X. And similarly, if Y is also a simple random variable, then expectation of X plus Y is equal to expectation of X plus expectation of Y. Well, this thing is a little bit tricky to show, be careful. Let me explain. If I write X as a simple random variable, which is equal to sum of AI's times indicator of the sets AI which are measurable, then from with respect to I from 1 to, let's say, M, and Y is equal to J from 1 to N, Bj times indicator of Bj. Well, here, this is in F, and this set is also in F, and small a and b are the numbers, okay? Now, we can write X plus Y as then double sum, Ij, AI, plus Bj, some indicator of AI intersection Bj. And we can suppose that here AI and Bj are partitions. I mean, we can suppose AI is a partition. Do you know what a partition is? As well as Bj. Partition means AI are 2 by 2 disjoint, and their union from 1 to M is equal to omega, and Bj is also from 1 to N is equal to omega. If this is, we can always suppose it by adding this lacking elements of partition to this set, to the sum, by putting as multiplier 0 here, okay? So it's not a restriction of generality. Hence, if AI and Bj are partitions, then AI intersection Bj is a partition, 2-parameter partition of the same space. Hence, when we sum this, we can write expectation of X plus Y, then is equal to sum, double sum, AI plus Bj times probability of AI intersection Bj. Now, I can write this as sum AI times probability of AI intersection Bj double sum here plus double sum here, bj times probability AI intersection bj. Here I sum first with respect to index, which is not at the bottom of I. So I sum with respect to j here. Then when you sum with respect to j of pi intersection bj, sum j varying from 1 to n, this is equal to probability of the, since they are 2 by 2 disjoint, from 1 to n, ai intersection bj with respect to j. Since bj's union is equal to omega, this is equal to ai. Hence, this is equal to p of ai. Okay, this is the trick. Well, hence, the first one is equal to ai times probability of ai. Similarly, the second sum is equal to bj times probability of bj. Hence, it's equal to expectation of x plus y. This shows that this expectation of simple random variables is a linear operator. It means that it commutes with the sums and multiplication with the constants. Okay, and another property which is the key property, and here we see the value of the Kolmogorov axioms in the definition of probability is the following. Now, if xn is a sequence of simple random variables, or simple real random variables, then and such that for fixed omega, xn of omega is decreasing to 0. So it means that the translation of this limit of xn of omega is equal to 0 for any omega as n goes to infinity, and this progression of the sequence is downward, okay, in decreasing way, decreasing manner. Okay, then limit as n goes to infinity of expectation of xn, it is also a decreasing sequence, and hence I am putting this arrow here, is also 0. Okay, so this is a very important property. This will give us the key to define the integral of x with respect to probability when x is not anymore a simple random variable. Okay, so let me prove this. This is, you'll see how it is important to use the axioms of Kolmogorov here. Okay, since xn's are simple random variables and they are decreasing, okay, since they are decreasing, as x1 is the largest one. And since x1 is a simple random variable, it takes a finite number of values, hence all its values are bounded by a constant. And x1 of omega is less than or equal to k. This is for any omega by definition of simplicity. Okay, hence when you look at this thing, let's look at xn. Xn is positive, and it is then less than or equal to x1, hence it is less than or equal to k on the set where xn is greater than epsilon. Epsilon is any positive number, plus trivially it is less than or equal to epsilon on the set on which it is less than or equal to epsilon. Okay, this is almost a tautology. Tautology means saying the same thing twice. Okay, since indicator function is upper bounded by 1, this is always less than or equal to k times indicator function of xn greater than epsilon plus than epsilon. Epsilon is an arbitrary positive number. Since xn is upper bounded by this random variable, and since expectation is a positive operator, then if I take the expectation of everybody, same hierarchy will be followed. Hence, 0 is less than or equal to expectation of xn, and this is less than or equal to expectation of this. This is a simple random variable, and this is k is a constant, k times expectation of indicator function xn greater than epsilon, and expectation of constant is equal to epsilon itself. Hence, this is less than or equal to that, and this thing is equal to k times probability xn greater than epsilon plus epsilon. Okay, now let me denote by Bn the set on which then xn is greater than epsilon. Okay, then I claim that Bn is a sequence decreasing to empty set, because xn converges to 0 as n goes to infinity for large n, then this set will be empty. Okay, so this implies that intersection of Bn's from 1 to infinity is empty set. Hence, we know from one of the properties of the expectation probability that since Bn is a decreasing sequence, then the probability of intersection of Bn's, which is 0, so sorry, which is 0, not empty set, this is 0. This is equal to limit as n goes to infinity, probability of Bn. I have proven this, okay? Hence, this is equal to 0, hence this thing goes to 0, okay? Hence, this implies that limit as n goes to infinity, probability of xn greater than epsilon is equal to 0. Hence, when I plug everything, then I find that 0 less than or equal to limit as n goes to infinity, expectation of xn is less than or equal to limit k times limit of these probabilities plus epsilon. Hence, this is equal to less than or equal to just epsilon. Since epsilon is arbitrary, this implies that limit of expectation of xn is 0. Okay, this is what we want to prove. Quota rata demonstrato. Okay, so this is one of the main steps of the thing of the construction of the integral, and the second one is just a consequence of this. Let me give it as a lemma. Let then Zn and Z be simple real random variables. And if Zn increases pointwise to Z for any omega, okay, then we have limit as n goes to infinity of expectation of Zn, this is an increasing sequence also, is equal to expectation of Z. When the proof is trivial from the above, we have just Z minus Zn is a sequence which decreases to 0 as n goes to infinity, then apply above result. Okay. Hence, as a consequence, we give another lemma. If xn and yn are two increasing sequences of simple random variables, if xn and yn are two increasing and positive simple random variables, such that limit of the xn as n goes to infinity, since it is increasing, the limit is always exists pointwise, is less than or equal to limit of the yns. Okay, I didn't say that the limits are simple random variables. They are limits of simple random variables, but the limit may not be simple. Okay, be careful. This is where the things is important. Then limit as n goes to infinity of expectation of xn is also less than or equal to limit as n goes to infinity expectation of yn. Okay, how do I do this? Well, the proof is not very difficult because we have prepared everything for this. And since limit of xn is less than limit of yn, if I take the limit of as n goes to infinity of xn minimum ym, this is minimum, it will be equal to xn. Okay, since xn also is a simple random variable, I can apply the preceding lemma, which says in this case that limit of expectation of ym, which is greater than limit here m, expectation of xn minimum ym, and this limit, since this limit is equal to xn, I can use the preceding lemma. This is equal to expectation of xn. This is m. Okay? Hence, we find that, hence, limit as m goes to infinity of expectation of xm is greater or equal to expectation of xn for any n. Since expectation of xn is an increasing sequence, this is also true if I take the limit at the right. Limit as m goes to infinity, expectation of xm then is greater or equal to limit. So this is, sorry, this is ym. Oh, I am sorry. Ym, this is ym. Okay, hence this is true for any n, hence I can take limit with respect to n. This is then greater than limit of expectation of xn. This gives the proof. This is very important because this result says that I can define, hence, this is the end of the proof, hence, I can define the expectation of a measurable positive random variable if z is a measurable, so is a random variable. In fact, I don't care, is a function from omega to r plus positive, and such that there is an increasing sequence of simple random variables increasing to z pointwise, then I can define expectation of z as to be limit of the expectation of xn's. The above theorem says that this limit is independent of the choice of xn. If I take another sequence of simple random variables increasing to z, then from the above lemma, we have the same limit. Hence, if I define, hence, the definition expectation of z or integral of z with respect to p on omega as the limit of the integrals, increasing sequence of integrals on omega of xn dp, this is a good, between quotation marks, definition. This is all about abstract integration, okay? And this is very important. As you see, I didn't use at all any topology in this stuff, except I have given a sigma algebra using the open sets in the final space, but this is really the minimum that we can. Okay, so this is the definition of the integral. Okay, and don't forget, this is extremely important. So I can apply this to integrate the random variables which are defined as omega. I will take soon as the space of the continuous functions on 0, 1 with values in RD. This is Bilkent's cause model basis. Okay, and I will apply all this idea in this situation. Okay, up to now, are there any questions? Because this is really an important point.
Notation is so crowded. Maybe we have to revisit the concepts after the lecture.
You have to study these things. Yeah. You should revise them. You cannot, if you had mathematical maturity, let's say if you have been a mathematician, working, professional, etc., then you could have understood maybe during the class, because what we are doing is essentially the same reasoning, showing that definition is insensible the way that we are defining, hence it's a good definition, okay? But since you are really at the beginning of your career, then you have to work a little bit at home. Yeah.
Hocam, can you save the lecture notes?
Sorry?
Can you save the lecture notes in your...
Yes, I will do it and I will send it to you.
Okay, then we can upload the website, our website.
Okay.
Okay, thank you.
Okay. Now, so I will just give today, but I will not prove it, one of the most important theorems of mathematics, not only the probability, it is called monotone convergence theorem, or theorem of Beppo-Levy. Okay, it says the following theorem. This is monotone convergence theorem or theorem of Beppo-Levy. This is really, really very important. It says the following. It is very simple. Let xn. Now I recall your attention, we have defined the expectation or integral of a positive measurable random variable, not simple, okay? Measurable only. I have just explained it. Now, this is the thing which completes this, the figure, the painting. So let xn be a sequence of positive, let be a sequence of positive increasing random variables, not simple random variables. Be careful. Okay, such that, well, since they are pointwise increasing, there is always a limiting function. It may be plus infinity eventually, that I denote by x. Okay, then theorem says that expectation of x, here plus infinity is included, is equal to limit of the expectations of xn's, increasing limit of xn's. This is what we call monotone convergence theorem. And it is at the heart of a lot of things in mathematics, not only in probability. For instance, in complex analysis, this is extremely important about harmonic functions, application of it. Okay, so I think I will stop here because I have charged you with a lot of things, and I want you really to study these things very well, and then I will give as an application of this dominated convergence theorem. This is the second important theorem of mathematics, convergence theorem, which says that if this scenario of monotone convergence theorem is not satisfied, but nevertheless there is pointwise convergence, but the convergence is not monotone increasing, it may be fluctuating. Okay, under which condition then we can commute? So under which conditions can we commute limit and expectation? This is the question. Okay, in other words, let me write it in quantifiers. Assume Xn is a sequence of measurable random variables with values in real life. Okay, real random variables, not simple. Okay, forget about the simple now. It's finished. Such that Xn converges to some x as n goes to infinity pointwise, sorry, for any omega in omega. Okay, so this is pointwise convergence, a weak convergence. Under which condition, when do we have limit as n goes to infinity, expectation of Xn is equal to expectation of limit of Xn. This has very, very deep applications. For instance, when you study the Fourier transform that you apply, I don't know, to solve some partial differential equations, etc., and you want to calculate the limit of the solution, then you commute limit with Fourier transform, which is an integral, hence it's an expectation. If your condition is not satisfied, then your generator may explode. There was a student with GPE, I mean, exam 4/4 from electrical engineers in Bilkent. He has tried to solve the telegraph equation using Fourier transform. He didn't know this theorem because I had flunked him in analysis courses. He has used this without satisfying this hypothesis. It was a disaster. Okay, so don't forget, this is a very important thing. Okay, the announcement of this theorem is that assume that there exists a positive random variable, positive, with finite expectation. If all the xn's on absolute value are bounded by y, then the answer is yes. This is very important for any engineer. I'm not talking about mathematics at all. You use this in a lot of places. Okay, so let's stop today. I think it's enough. So next time I will prove these two theorems and I'll give some very deep applications of it using law of large numbers. Okay, any questions?
Thank you for
Huh.
thank you for this lecture, William.
Okay, is it? Can you follow or not? This is what I would like to know. This is the first time that I am doing such a, let's say, such a thing as we are in the United Nations talking to different people.
Maybe it seems to be a little hard to follow, but that's the first lecture. Then maybe we can overcome it.
I didn't hear very well.
Okay, hocam, yani that's first lecture.
Huh.
It seems to be hard to follow.
Uh-huh.
Yeah, that's why I hope we will study on these concepts. Then maybe for second lecture is.
Yeah, you have to study these things. Definitely, this is really olmazsa kısmen. I cannot bypass this thing, and it wouldn't be honest then to pretend that I can teach something without you knowing these things.
Okay, hocam, and we will continue with Ito calculus 2 weeks after. However,
yes, Ito calculus, but it will not come immediately. First, I will do Ito calculus in discrete time. And
okay.
Discrete time will be a very good preparation and application of these things and good preparation for the continuous time. Okay, so I hope that at the end we shall arrive Ito calculus continuous time, and I will give Ito formula, its application to this, all the things that I have spoken at the beginning.
Okay, hocam, next week not our lecture for Ito
No,
calculus.
next week no lecture.
Yeah. However, there will be a first lecture of dynamical systems for next week. If you're interested, you can also join this lecture.
What is the subject?
We will start with dynamical systems, but I don't know.
Well,
I'm not moderate these.
okay. Well, if you know the outline, please send it to me. I don't want to come for the beginning.
Okay, I will send.
In fact, there is an intersection with Ito calculus and dynamical systems. When we shall advance, you shall see it. In fact, there are random dynamical systems, a kind of differential equation, but there is a random input also. And you study the stability, these kind of things, orbits. It will. I will explain it later on.
I'm not sure about the status of dynamical systems.
Okay.
I will send the website of.
Okay, so I will send you the notes of this lecture.
Okay.